I'm sorry, I am desperately trying to figure out how to double up on Twitch and YouTube right now. So it will be a moment. Please enjoy this looping music that will definitely not drill its way into your brain in the meantime. Just one more moment. Alright, this is getting into my head too. Oh, that's not our one. There we go. Yeah, this is not properly set up, but I figure streaming through 2 platforms better than streaming through 1. And it was supposed to be playing different background music now. That's not even the background music it's supposed to be playing. Hey, it's Poisson and Variants. You're a mathematician and me. Why is that video starting at the end? Hold on a minute. There we go. And it's not even in the slideshow. Oh my god, it's so magically scuffed. It's so wonderful. It's so bad. Hey, it's Poisson and variants. Alright, hey, it's Poisson and variants, your mathematician and vtuber. Here today to talk about metric spaces, and Twitch chat is not showing up on my overlay. Awesome. I can see it though. That's fine. That's what matters. How is everybody doing today? I hope you're all doing well. I've been doing well. I woke up at like 3 in the morning. Yeah, I woke up at like 3 a.m. this morning. And yeah, that's pretty much how it's been going. But I decided to do it. Start a stream that I had planned only 24 and a half hours prior. I think that's efficiency right there. I don't know. No, it's, I was getting yesterday, but what happened was I was feeling pretty low energy. Was pretty much, I had really low iron and really low protein or something, I don't know. But I would like try to stand and then I was just like, yeah. So, got price? I don't understand that joke. But today, I would like to go through a very small presentation. Price. Oh, with a Z. I would like to go through a very small presentation I made. For metric spaces. And granted, this would probably work better with more people willing to ask questions, but I don't care. It's gotta start small somehow. And then after this stream, I can figure out all the logistics of how Twitch and YouTube I can stack on top of each other, because I don't think it's gonna be easy at all. In fact, I think it'll be quite painful. But scuff makes the world go round. Scuff leads to success, as the saying goes. I think Newton said that right after he invented gravity for the price of an apple. And to start with my own, I need to hold on a minute. This has been my joke for the past like 2 streams. Want to hear my perfect imitation of a soda can or a Red Bull can opening? I'm really good at it. practice this. I practice this a great deal. Alright. Boom. Perfect. I hope that even registered on the mic. It's my first caffeine today. I even bought coffee yesterday. And for some reason, instead of making coffee this morning, I was like, you know what? Let's instead have a Red Bull because that's healthy. It's fine. It's sugar-free. It's extra healthy. Alrighty. So. Oh, God. Oh, no. What's happening to this window? Okay. What the hell? Ah! Oh, there we go. Fixed. Perfect. Flawless. So today, we are talking a little bit, and an emphasis on a little bit, because I didn't make this very long. But the very, very basics of metric spaces. And that will be with me, your host, your host, I guess. Poisson invariance. Aforementioned mathematician and vtuber. Oh, that's appearing on screen. That should not be appearing on screen. So first and foremost, hello. This is me. This is Poisson invariance, mathematician, vtuber. That's my face. That's my face. That's my eyes. That's my headphones, but a different color. Oh my god, I don't have a headphone attachment on this model right now. I thought I did. Wait, did I? Whatever, I thought I had my headphones on. Where are my headphones? Where are my headphones? This takes priority. This absolutely takes priority. I don't know where they went. Oh, no. No, they're called... yeah, 0 FPFs. Now I have to try and put these on. Yes, I know. Live 2D works. Good enough, good enough. Okay. Perfect. Okay, perfect headphones for sure. Now, we are going to, so as, this is scuffed. Poisson variance, your mathematician, VTuber, yada yada yada. This is me. I have my headphones on now. And today we'll be talking about metric spaces, which is an introduction to the concept known as geometric analysis. And I'm sure everyone has heard of geometry. 24 and a half hours late, but don't worry. Geometry. We know geometry. Geometry. I posted about it. I said I wouldn't be able to make it. I wasn't feeling well yesterday. Aurora. But I did say I would, so apologies. So geometry. We've heard of geometry. These headphones are annoying me because they're not lined up correctly. But shapes, polygons, nonagons, all the fancy stuff. And why do we care about them? Because everything in life is a shape. My headphones fixed now. That's better. That's better. Okay. Everything in life is a shape. Be that. I don't have examples off the top of my head. I didn't really practice this. No, but triangles are like some of our strongest shapes. We have nonsense shapes, which just make up, like, for example, conglomerations of, like, bacteria and whatnot. You have rectangles. People freaking love rectangles. They love to build in rectangles. You have ovals. You have stars. That's what it is. You have all of these shapes that can do anything. Literally everything in existence is in some way a shape. And additionally, we have the concept of analysis. Analysis, or as we call it, the, analysis. looking at information and taking in that information to try and understand it the best we can. Real analysis, geometric analysis, is literally an understanding of the world, the understanding of existence, and it's all of its components, because that would be important, but specifically from a mathematical standpoint. Welcome, Jan! And that's important because people can look at things and not understand them, or understand them on a base level, or understand them conceptually, or understand them generally. But if you don't understand the numbers behind them, oftentimes that can cause some level of problems. Don't tell anyone that I have a great deal of companion cube thought process when off stream. It'll look bad for my ratings. The CCC will catch on. That all was an example of, like, statistics, though. This kind of stuff. That is more like statistical analysis, but it's the kind that, like, people would know. Because I could look at a shape and be like, yes, that triangle is a triangle. That rectangle's a rectangle. That flip is a flip. That's cool and all. That's great. But until you get numerical, that, or add some sort of number base, generally, it's hard for people to wrap their heads around that. So, I figured an example with more conventional graphs and statistical thingies would be statistical imaging representations would probably be better for people to understand. Today we are looking at the basics of metric spaces, and as I said, that was all statistics. But what we want to focus on is spaces to start, because in order to talk about analysis, you have to talk about metric spaces. In order to talk about metric spaces, you have to talk about regular spaces. All right? And when I'm talking about spaces in general, well, I'm not talking about space. Astronauts. This looks AI generated, I'm just realizing. I am sorry. I am sorry for using this image. I use it like 4 times in this. I feel bad now because I don't want to use any AI generated images. I hate that kind of generative AI. I really don't like most AI in general. Like, I get its use in a lot of ways of, like, templates. That's really useful, but in the same way we have those kinds of templates. But anything that's, like, imaging, well, a vector space is actually a type of metric space. Are my eyebrows raising, registering? But no, I'd rather not use anything AI. But I just Googled space. I Googled space and got this. I don't know what happened. But no, we're not talking about astronauts this time. We're talking about these types of spaces. If you have done anything like calculus, then you're probably familiar in some regard with these types of spaces. Okay? These types of spaces encompass things like the real numbers, which Rn is all real numbers in n dimensions. And I can't use ChatGPT if I take the correct any question. The thing about ChatGPT is that it has trouble with any higher level mathematics. That's a place it kind of struggles. There's been a number of examples where, what was it? I was working with someone and they tried using ChatGPT for a differential equation, and it has some trouble there. It also has trouble with precision, because it's not designed to be a math solver model. There was an example where essentially how it works is if I follow a number of steps that says solve for like x equals 2, it will, it has its database that it's reading from, and it will go ahead and solve for that. Give you the steps of like, oh, I know I move over the 2, I know I do this. The thing is, the reason it knows that is because other people have done those steps. It doesn't actually understand the concept of balancing the equation or whatnot. It just knows the phrase balance the equation. I don't know if that's the case for all models, but I'm pretty sure that's the case for, I don't want to say no, I don't want to say anything definitively, but I'm pretty sure that's the case for like ChatGPT. Exactly. So when you start throwing less common things at it, then it starts to get very confused. Because I asked why it sucked and it said that. Well, I'm glad to see it's reliable then. Thanks, ChatGPT. It's like when you like... Here, I'll do it now. Hey Siri, are you listening to me? Similar kind of mindset. I guess because I was using, I don't know why, but it didn't read out loud, but it was like, I respect your privacy. Okay. Yes. I don't think you respect my privacy at all, Siri. But, yeah, so it doesn't necessarily, what's the word I'm thinking of? My brain is I'm out of it as heck today. Better use Cloud or Gemini, they have better thinking. It's funny enough, Google actually gave me 2 free terabytes of Google Drive storage because they also wanted someone to use Gemini. They're like, we'll give you Gemini and 2 terabytes, just use Gemini. And I'm like, no. It got really annoying when I was trying to write code in their Google Collab notebook, because I would try and start a new line, and then every time I tried to start a new cell, it would try to use Gemini to do stuff, and it was like, I was generating like a data frame, and it's like, all right, now that you've generated the data frame, do you want to look at it in this graphical thing? And I was like, no, I'm trying to generate this data frame so I can pass it on to machine learning. It doesn't know that. It's just like the most common usage is gonna generate the data frame and then look at the data frame. And it's like, yeah, I'm doing something a bit higher level with that. I've never used that one. I know, like, Vettel, I don't know if you know Vettel, the creator of Neurosama, has done stuff with, like, I think he's used, like, GitHub Copilot or whatever it's called for, like, working on Neurosama. And so because that one specifically just trained on coding for coding. So yeah, it would make sense that it's better than, but Yeah, I've never used Claudier, however you pronounce that. Regardless. Oh, she's really cool. So she's an AI example of is Cursor another AI one? I don't actually know that one. Oh man, we're gonna deviate from our usual programming. Cursor AI. Enhance developer productivity, AI for encoding environment. Claude is the pronunciation. Okay. Claude AI. Yeah, I've never seen this before. Okay, cool. Interesting. But Neurosama is an AI VTuber who's like an LLM that has been trained for a number of years now, and it has like a memory and is able to interact and is a pretty amazing example of AI in action. Right. Because ChatGPT is just a universal grab information kind of thing. And I don't know if it was, but I know that for a while it had like a... Am I bleeding? No, not bleeding. Cool. VTuber's going jobless now. No. So she's the one. There, I guess there's probably a few examples of it, but she's like the one like known example, and she costs quite a bit to keep running. And so, like, it's not practical to have her running if you're not a large scale person with high income. And like, at one point, I don't know if it was, I think it was for a certain month or a certain year or something, she was literally the top viewed female streamer on Twitch, and so Vettel definitely has the money to keep running her. But she's not something I have a huge problem with, just because she's something that is slowly advancing in creating and frequently collabs and interacts with other people. And Vettel as a creator is a really good person. I don't know. It's mixed. It's mixed. To each their own. Oh, sorry, phone pop up. Okay. But. That's a great example of just losing track of time, rambling. That's fine. This isn't a long presentation anyways, so this is going to be a 90% rambling stream. Oh, there. Okay, you know, I'll get. There's something, but I will get to that later. Setting that aside, spaces. Spaces entail things. How we think about them mathematically is, like I said, n-dimensional real numbers, n-dimensional complex numbers, n times m-dimensional matrices. And those numbers we frequently see, it's the application of real life things with numerical values. And a pretty frequent place you see this is in data analysis or like machine learning or something, where you have for example, a single data point. And that data point can have 10,000 features that identify it. Because you decided to look at the texture of the data point, you decided to look at the wavelength of the data point, you decide to perform a series of analysis on the data point, and then look at that. Perhaps the data point is made up of multiple sub-data points, and so you decide to take the mean of those, the standard deviation, multiple standard deviations, you know, plus or minus 1, 2, and 3 deviations, yada yada, that sort of thing. Great. So, in essence, how we would think about a space is where stuff is. You know, it literally is just a ball, or not even a ball, a cluster of information, which is something that wasn't explained super well to me when I first learned it. Now, don't get me wrong, the person who taught me real analysis, I love. He was my favorite professor. He's still the favorite professor that I've ever had. But he basically a vector with n factors, taking n recordings of data point, using average to display each pixel, but that would be very inefficient. Sometimes, though, that's kind of what you have to work with. So, like, recently, or in my paper that I did, that I just had published, I had things that were like, we took a sample. That sample we then chopped up into, I believe it was about 300 different mini samples. So we took a sample, chopped it up into 300 tiles. Those tiles we then performed analysis on. But we wanted information about the sample as a whole, as well as the ones that are about the tiles. So we took information about individual tiles and had them linked to the sample they were from, and we performed analysis on those clusters of tiles. Then we concatenated those tiles and took averages across the behaviors of those different tiles, and then used those averages to then perform analysis on the sample. A good example of how you have to be in very high dimensions. And the thing is, each tile came out to one data point. So if you try to represent it 2 or 3 dimensionally, it's kind of messy because you had to use stuff like PCA, principal component analysis, which has to do with like eigenvalue, or the leading like eigenvalue, to try and make a visual representation. I'm not a big fan of stuff like PCA though, because PCA or ICA, because it's a somewhat of a black box method, because it is just kind of like a bit less so than like SVM. Why would I need such a detail for a sample? Well, so what we were looking at is we were looking at cancer images, histology images. And the thing is, if you have a bunch of these tiles and samples in general, to the naked eye, a lot of these samples just look like hunks of pink, some red, some purple, some white. It's just this mass of kind of nonsense. And we were looking at the texture and the information of these samples. And so we wanted to look at it from a specific method, and that method entailed using multiple different color spaces and multiple different, because it was a color-based method for imaging. And so it meant that we had to essentially, we weren't sure what color space would have the valuable information. So we had to use a color space that was like, okay, let's try RGB, let's try LAB, let's try HSV. So you had to kind of cast a wide net, and that's often the case of you don't know exactly, that's the thing that like deep learning models do a lot, is that you don't know exactly what features are going to be important. If you did, then the analysis wouldn't really be relevant. Basically a Fourier transform with electromagnetic waves and better imaging. Oh, I didn't know about that. Oh, it's like a is it related to MRI? NMR imaging, also known as magnetic resonance imaging, MRI, is a medical imaging technique that uses magnetic fields and radio waves to create detailed pictures of organs and tissues within the body. Well, so in this case, we were looking specifically at histology images. And the reason we wanted histology images is that histology images are one of the most frequently used medical imaging formats, because what they do is they literally take a slice of the tumor and then throw that thing on a slide, and then ideally, so there are two ways they do it. They either freeze it or they conceal it, or they enclose it in a paraffin wax. And if they enclose it in paraffin wax, then they can it maintains a lot more of its structure. If they flash freeze it, then it loses some of its structure. It's an interesting little thing. But that's beyond the scope of what I was doing, because I wasn't brought on for the biology, I was brought on for the math. Which makes sense. I'm a mathematician, I'm not a biologist. But it was important that I understood a lot of how the biology works, at least some of the process, so that it can justify, when I'm writing this paper, why we're using the FFPE, the paraffin images instead of the flash frozen images. Because the flash frozen ones, as mentioned, can cause warping when the freezing process happens. Anyways, so the point of the study had to do with, chopping off. We have all these tumor chunks, and that's one of the most commonly used types. So amplitudes of wave blasted on a sample or recorded on a certain screen, I forget the same, and then probability to find the most probable amplitude and component ways to restore high quality image. Yeah, so a Fourier transform. That's actually not a bad idea, but part of it was that my mentor, the reason he was, the specific thing we were looking at was image texture. It was less about finding certain things, but it was more about using specifically the texture properties on like Harlick features in order to justify it, or in order to identify it. And the reason we kind of doubled down on texture is because, unfortunately, my mentor who brought me on for that project, give me a moment. That mentor passed away, and so ironically enough, due to cancer. And this was one of the last projects he ever did, and so we were adamant that we wanted to see his project to completion, and he was correct about texture being the identifying component. So, yeah. Anyways, sorry. But the point of a space is that, so that whole thing that the whole rant would be an example of a feature space. And that one is exactly what it sounds like. It is an n-dimensional space where your dimension is determined by the number of features you have, and then you just throw a bunch of samples in there. So, if that is in fact what we mean, a space is just where stuff is, then I have to take back what I said previously. That is in fact the type of space we're talking about, because that is a space where stuff is. It's just things that are assigned. So like, this satellite has a certain numerical value. This astronaut has a certain numerical value. This planet, this planet, this planet. I wonder what that planet is. I want to say Kepler 22b. Anyways, these things all have a numerical value. And so it's that same sort of thing where now this will be represented by a more negative, closer to zero. If like down here is the origin, this will be represented with closer to zero. This will be represented more on one axis, but about the same on another axis. This will be represented greater on both axes. Yeah, it's if you were to replace this all as like a big graph, it would be pretty clear. So now that we've defined what a space is, yay, space, a space in space, let's now also look at the other half of a metric space, which is the metric. And a metric is pretty simple. A metric is just a measurement. Like we have the thing known as, the metric system. But space may or may not be empty like the one in image, so it'd be messy to work with. Space! Well, it depends on the type of space, really. And that's the thing is, you can actually, so, just hop back into that, yeah. As one of my professors would put it, you don't have to work on a God-given coordinate system. We're very used to something that, the defined kind of Euclidean XY kind of coordinate system. And that's, you don't have to work on that. You can shift, you can change how your space looks, you can change how your space functions, so that this astronaut actually has a greater value than this astronaut because you flipped the metric, or you flipped the direction of the space. Or you could do something like the color intensity of this, or the size of this cluster is greater than the size of this cluster, so this one actually has a higher value. That's the cool thing about spaces in general. Working on empty space will not be accurate, IRL, especially in physics. So that's where physics, you want to, how do I say it? You want to start off with this is kind of why they start off in physics with the base assumptions of like, you assume no gravity, or you assume only gravity, you assume no drag, you assume no friction, you assume no momentum, kind of things, because you want to build up this concept of working in a generalized space first. I've always had mixed feelings about that though, because a physicist wants to work applied from the get-go, but it is important to have a base understanding. It goes back and forth. Really, the entire way that so much of STEM is taught is imperfect. Linear algebra is a great example. Should I learn linear? Because you can technically learn what matrices are back in algebra courses, solving systems of equations. Okay, but then you don't actually touch them again until linear algebra. Personally, I actually never interacted with matrices when I learned algebra, but I've seen people who have, and I'm like, you're working with matrices this early? They're like, yeah, it's just solve a system of equations, because that's all like a lot of linear algebra is. But working on 2D space is a pain in physics, especially under multi-body dynamics. Yes. Yeah, because in a 2D space, you are taking a lot of assumptions. funny enough, that's actually a really good point. You see a lot of, like, intro to physics problems have a 2D setup, but you'll never see that really in the real world. Because we live in a 3D world. That was actually one of the things. Yeah, those kinds of things, though, are why I never really took more than, like, 1 or 2 physics courses when in college, because I would always get caught up with, like, model creation. I'm like, what do we assume? What don't we assume? I really like the more conceptual of being able to create my own space like that, like create my own metric space, create my own vector space, create my own n-dimensional space, and work in that numerically, rather than have to exist in a physical space where I am forced to act under certain things like gravity, like friction, like momentum, all that. That said, if you take those assumptions and convert them into a concept of just a function, this is where I find the crossover is actually helpful. If you're looking at it from a point of view like differential equations, I gotta fix my model real quick. In differential equations, when you're crossing over and saying that you're just viewing friction as a negative coefficient instead of having to view it as a model, I find that much easier. If I can have a function that defines everything, I can work with that so much easier. And that's why, funny enough, actually, in physics, I can work with all the vector-based stuff in physics completely fine. And it really is the thing that gets me, is the model creation. Because vectors being onto, vectors projecting onto one another, that stuff all works great. You know, you separate your X component and your Y component, you have those behave differently based off your corresponding forces, that's all fine. It really is, I like set up a model, I'm like, what assumptions am I supposed to make about the universe? Because this isn't a space I created, this is a space I was given. That's my rant about physics. Let's celebrate the conclusion of that rant with a Red Bull sip. I'm proud of myself, because I've not been eating ice recently. Eating ice is a byproduct of pica, which is a byproduct of iron deficiency, and I have very low iron. And so the fact that I haven't been eating it is good, because instead of eating it to feel like I'm eating something, then instead my body turns to eating actual foods. And so I'm like, what if instead I had a salad? Anyways, space. We are in space. Space! And as I mentioned, this is a good example of, yeah, physical space, but we can apply any value we want to anything in the space. But in order for a space to follow most mathematical rules that we care about, and a vector space is an example of this, we want a metric, a form of measurement, in order to define the space as more than just a collection of stuff. So a metric is specifically where two things have a measurable distance. Now, if we're measuring the distance between 2 points, like the metric system is called that, because it just literally means measurement system, which is so funny to me, because it makes, like, yes, we should just use metric. I hate that my brain is so wired to imperial, because that's what I was raised in the US, and so my brain is wired around imperial. So I intuitively know how big about 5 feet is, but I don't intuitively know about how big, okay, no, 2 meters is easy. Like, I can, a mile versus a kilometer kind of thing. I know the conversion of inch to centimeter. 1 inch is 2.54 centimeters, but I'm not used to measuring in centimeters. So when someone says, like, because I think I'm like 170 something centimeters tall, because I'm 6 feet tall, so I don't, but I don't intuitively know that. That upsets me that I don't intuitively know that, and that's something that I really just have to train my brain on, because again, all those conversions are fine. I don't even know how heavy 1 kilogram should feel. That's true. Well, so I am incredibly skinny armed. I am very skinny. My God, I looked at myself in the mirror. I like, there's a full body mirror upstairs, and I walk upstairs and I like turn, I'm wearing skinny jeans, and I'm like, oh my God, I am literally a twig. But, if you, a skeleton, kind of, yeah, pretty much. Yeah, absolutely. There was a long time where my my younger sibling would be like, shut up, I don't want to hear that from a twink, and I'm like, okay. They would just but anyways, SCP-069, let's find out what that looks like. I don't really know any SCP stuff. I've played there's an SCP game though that's really fun. Oh, do you mean 9-6? Because this... What the heck am I looking at? Just remove that. You have the strength to back up your skinny body. I do not. I've started going to the gym, though. That's less about strength, though. And that's more about just being healthy. Turns out, though, I have a way higher cardio than I realized. And like, I went to the gym the other day with my brother, who goes pretty frequently, and I was able to just like do a 30-minute run without any real issue, and he was trying to keep pace with me. And I'm like, I never exercise, but apparently I have great cardio. That's not true. I go on walks. But what day is it? Is it Monday? Okay, after stream, since it's Monday, after stream, I should go to the gym, because Mondays are the perfect, or like weekdays are the perfect day to go to the gym during midday, because it's just old people. And I really don't want to deal with gym bros. That's the thing, I don't dislike gym bros, but gym bros are not exactly my community. And of course, anxiety is like fear of judgment for it. The thing is, everyone at that gym is actually super nice. The gym community, I found out, is super nice. Which I just had no idea. Like, you think of the gym community as like jocks in 80s movies. You're like, skinny nerd, You skinny nerd, I bet you're a nerd. Bet you wear glasses. I don't actually, no, I wear glasses sometimes. I haven't needed to wear glasses in a while. Anyways, but no, everyone I've met at that gym, super nice. Super, super nice. It's such a live and let live mentality. Cause like, I'm not religious. I'm an atheist, and my and this gym dude I met, he was like raised evangelical Christian, and we're talking, and we have like, there's like zero contention. It was really, really nice. He was just like, oh yeah, you know, it takes all kinds, kind of thing, and I really appreciated that. Because yeah, the kind of passive assumption about a lot of gym dudes is this idea that yeah, they're jocks, but in reality they're just like nice people who want to help each other. It's this really nice community of like people who want to help each other get better physically and help strangers and whatnot. And they're like willing to help you if you don't like. I was using a machine, and then this dude introduced himself to me as he came over, and he was like, "Oh hey, I saw you were using this machine. Do you want some pointers on how to do it?" And I was like, "Yeah, sure." And he's like, "Oh yeah, so you want to do it like this, da da?" And I was like, "Oh sweet, thank you." He was super nice, and that's how we started talking. Too much math, not enough toasters. I was playing Stellar Blade last night. I was just doing more side quests. Stellar Blade, I'm probably going to continue on my own because I don't think people care about that, which frees up time to stream other stuff that people will be more interested in. But I was playing Stellar Blade, and I found a coffee maker. I didn't find a toaster, but I did find a coffee maker, so we're getting close. We're getting close. Don't worry. The second I find a toaster, I will absolutely clip it, and I will send it to you. I will send it to the Discord chain. Don't worry. Okay. But metric system. No, not metric system. Metrics. So, a metric, as mentioned, is just the measurement of distances between 2 points. That is good. We like that. You want to know what the distance between two different objects is so that you can compare them. That was part of why a space matters, is because you want to know how you're actually comparing these things. And what's important about a metric is that, first, it has 3 different properties. The first one here is that the distance between 2 objects will always be greater than or equal to 0. Namely, you cannot have a negative distance. That being said, that's why vectors are defined as their direction and their magnitude. Flamingos and hot dogs. Okay, so you're on Imperial. Just kidding. They use cows, football fields, and the only thing I see yards ever used for is football. Does anyone know how? Does anyone use a yard for anything besides a football field in terms of measurement? Like, I know it's 3 feet. It's about a meter. But like, that's it. Washing machines. Do people measure washing machines in yards? What? Or do they measure with washing machines? A yard is 3 feet. For sewer hole length. Okay. See? There had to be something out there. It's funny, it's sewer hole length. It's really funny to me that a yard is about a meter, but it's just slightly different enough. So if you add them together enough times, it will become notably different, but on an individual basis, it's approximately the same. Oh, because you have 3 yards, obviously. 3 yards per yard. You do, yeah. That's exactly right. You have 3 yards in your yard. That's such an American thing. It's about 7 cows wide. That's about 3 football fields long. Imagine a 747 on top of another 747 that's a bit smaller. So I guess a 737? I don't know. I don't know aviation. Something that popped into my head just now. Flamingos, hot dogs, yards, solar 3, 4, I don't know. I don't remember what it was. You got out of high school for the summer, you don't want to talk about math. I have bad news for you, Shane. I'm trying to make my eyes be like, I don't know what I want to do with my eyes, but mathematician and VTuber. I'm sorry to tell you. If you sit through this, eventually I'll play FNAF for you. So I was gonna say something about speed. 30 funkers, 8 elephants, and 2 toaster long road in Texas. I'd be curious how long that is. That's about a ratio of 7.5 football fields to 1 Great Wall of China. Yeah. Nerds are kind of the whole shtick. I thought that was a given. But oh, vectors. Vectors are, measured by distance, or by magnitude, direction and magnitude. So, the direction will determine positive or negative, but the magnitude must be greater than or equal to 0. And if it's exactly 0, then the 2 points we're measuring the distance between, or the magnitude between, sort of, I say distance, is, are equal. That is what our first bullet point of our metric says. Oh, and by the way, this P here is rho. This term is generally used to say the rho of xy is the distance between xy. And rho we can define as anything. It's just kind of we tend to use it to mean distance. Know how to work in fax computers and VCRs and CRTs, and even I'm not sorry. Everyone specializes in different things. That's the thing. The thing about things is that everyone's thing is a different thing. So even if you thought that one thing was thinking about that thing, well, think again. Because the thought process of ignoring that thing is you don't want to ignore that thing. You want to do that thing. You want to put some thought into that thing, so then if you think about that thing, it will no longer just be a thought, it will be a do, because you can now do that thing because you thought about doing that thing. What? Where am I? Who are you people? Anyways, so you specialize in sleeping. I don't, I have insomnia. Stop making fun of me. I'm undiagnosed, but I'm pretty sure. I believe that's actually a religion, Aurora. So, the second important thing about a metric is that the direction will determine positive or negative, but the distance between the 2 points, regardless of how I measure it from x to y or y to x, point A to point B or point B to point A, is the same. The distance between, Houston and DC is the same as the distance between DC and Houston. That being said, that doesn't mean the travel time would be the same. It's things like uphill and downhill and whatnot, that is not taken into account by just the distance, but by other factors as well. Procrastination is religion. I mean, you practice it? I'm trying to think. How do we define a religion? It's -6, probably. But we just determined it can't be negative, so it would just be 6. What's the official definition of? Are you tax exempt if you're a procrastinator? Oh, I need to start the Church of Mathematics, and then I can run a tax exempt lecture hall. I'm a genius. Where do the 10 calories come from in this Red Bull? Do you know that's a common misconception? People always focus on the calorie count of food. And while it is a good representation of certain things, the calorie count is not the most important. But, oh, you have a spoon you've had since the 4th grade? Amazing. Amazing. The 10 calories in Red Bull comes from the wings. That's why, I absorb the wings and then they like sprout out of your back. Like body horror. They like burst out of your shoulder blades. Kind of cool, actually. That actually sounds kind of metal. Ferb, I know what I want to do today. Body horror. But no, the most important things to look at are stuff like sugars. You don't want to pay as much attention to calorie count. And it's true that calorie count can be a great way of understanding how you weight loss through stuff like Ozempic is a great example of the importance of calorie count, or the usage of calorie count as a good metric. Well, did he fly? Did he get wings? Okay, good. I'm glad he's fine. No, but so what you do is your body gets used to consuming a general amount of calories because you're used to intaking a certain amount of energy in. So say your Ozempic is generally used for heavier people. So say you're a big guy, you're a big person, you're large, you're not big boned, you are in fact just heavy. So say you're consuming 3,000 to 4,000 calories a day. Your body is used to that. So that's why if you try to just consume less, then your body hates it. This is why for heavier people, I learned. So this is something I actually didn't know because I was skinny. But I was talking to my coworker who's a bit on the larger side, and he was telling me about how his body craves food like crazy when he's hungry. It's not something he can just ignore. And as someone who's very skinny, it's something that I can just ignore. And I never realized that. I was like, yeah, I could go an entire day and eat lunch and that's it, and I wouldn't care. I would probably be a bit hungry or a bit peckish, but it wouldn't be a deal breaker. It wouldn't be the end of the world for me. So if he's consuming 3,000 to 4,000 calories a day, his body is so used to that if he tries to consume less, his body goes into a panic mode. It assumes that he is consuming, he consumes 2,000. It assumes he's only consumed half of his required amount. But that's actually going to be more about metabolism. Because, I have a very high metabolism, and I can eat like crazy, although my appetite in general has decreased a lot, recently. And don't forget that eating can also, be a form of entertainment, in a sense. Sometimes you do eat just because you want to. It's fun. It feels good. Eating is enjoyable. Our brains are trained to like eating for survivability. But as you're ingesting 4,000 calories a day, and so if you don't get that, your body goes into a panic state, and so it requires that you ingest that extra amount. And so in order to burn off, so how something like Ozempic works is that it, limits your appetite. I just don't want to open the book, so I slowly eat food. Anyway, so it limits your appetite and tells your body that it's full. So after 2,000 calories, your body still burns the daily 4,000 calories. So it essentially what it does is it's burning half the calorie amount that it would, or it's burning more than it would. It's burning the same amount, but you're ingesting less. So over time, you're just burning a lot of calories. That's why calorie count is so useful. But the things that are actually adding weight a lot is stuff like sugars. Like soda is a great example. If you drink a ton of soda, you're gonna gain a lot of weight because that's just a ton of sugar that goes nowhere. Will you die if you eat too many tacos in one sitting? Probably. Over the course of you're gonna die no matter what. That's life. I'm gonna die. You're gonna die. If it's you, it could be him. It could even be, and then my head explodes because Meet the Spy is funny. That dates me. Anyways, the longer I eat, the more I sit idly and calm my head. I'm very prone to anxiety attacks. That's a good example. Yeah, if eating is calming to you, that's fine. That's not uncommon. I find that recently I've found that I'll make some food, and then because I'm house/dog/cat sitting right now, I'll make a small dinner, and then the dog and I will sit on the couch, and I will just play YouTube on my phone, and I'll sit there for just half an hour slowly eating, and yeah, that helps calm me down. And if you are prone to anxiety attacks, Aurora, I would highly recommend seeing a specialist. A common misconception, it's important to go to a doctor, go to therapy, these sorts of things, because therapy, I like to think about therapy as I say this as someone who's only ever gone to therapy once and didn't go back, but ignore the hypocrisy. Anyways, therapy is like a brain massage. There are times you just need a massage. A massage is good. A massage is great. Yeah. You don't necessarily need a specific problem. If your brain is going in certain directions, talk to someone about it. You don't even need to go to therapy. Sometimes it is just talking and be like, hey, I had a bad day. And they're like, oh, okay, try this. That is rough. That is a high standard parenting kind of situation. That's tough. I remember you telling me about your situation with your sister, and so that's part of why. Dang. Okay, well, there are other methods, even if you don't go to a specialist specifically, to dealing with those sorts of things. Just finding habits that help calm you down, like you said, like eating. Well, in that case, that's why you can relax with an anime boy on the internet who talks about numbers. And that sort of thing would also explain why you like feel the way you do about like video games and whatnot. That wasting time is anxiety fueling. I can't really play video games if the video game doesn't have a set objective. If I can make progress and complete it, then I can play the video game. If the video game's something like Minecraft that's aimless, I can't do it. I know technically you can beat Minecraft, but it's more about the creative stuff, and I'm not a very visually creative person. Yeah, and that kind of anxiety is also like what's affected me a great deal in my life, which is why I would have stuff like insomnia and whatnot. That's not uncommon. Breathing exercise. Do you exercise? Exercise is a great way to deal with that kind of stress. And if you don't feel great physically in general, like even if you're like your body is healthy, sometimes, or like you have a high metabolism or something, like you don't need to work out, it can still be important to get that exercises, even if you're not trying to maintain a certain like figure or anything. That kind of stuff is really important for your mental health. Going outside as much as possible. You know what? Studying, like if you study at home, don't study at home. Go to a nice library, go to a nice coffee shop, go to a nice third place. And then study there. And it will probably be much more enjoyable and help relieve some of the stress. And if you have companions that you can study alongside, cohort members, then do so. It feels like it's a waste of time. An important thing, though, is that you'll never be able to get over that feeling unless you do it. You do online coaching. I feel like that could be a hit or miss, because the online component does set a barrier, because there is studies that suggest that physical proximity is very important. Up to about 2 to 3 meters away from one another, you start to see benefits. You want to, that's why working in person actually, for a lot of stuff, actually does have very strong benefits. Especially in terms of collaboration, in terms of understanding, in terms of feelings of positivity. Those go a long way when you're within a physical proximity to one another. And it's true, the internet has made all of that stuff very, very convenient. And it's really funny. I understand the irony of me, anime boy, on the internet, streaming, talking about being in person and not parasocial, but in my defense, I'm gonna go to the gym after this. Am I gonna talk to anyone at the gym? Absolutely not. I will have earbuds in the entire time. But I don't remember the point I was trying to make. Those things are really important. Anyway, metric spaces. Yeah, we're definitely on topic. So, the second bullet point. So the first bullet point was that the distance between 2 points has to always be greater than or equal to 0. If it's 0 exactly, they're the same point. The other one is that the distance between point A and B is the same as distance between B and A. The example I used was the distance between Houston to Washington, D.C. is the same as the distance from Washington, D.C. to Houston. We're not talking travel time, we're just talking literal distance. Travel time is where you would get stuff like velocity, you would get, that gets more into physics. based off the different barriers and whatnot. The same way that like flying across the country can take 4 hours in one direction and 3 hours in another, because like you're going with the airstream, the jet stream and whatnot. It's pretty cool concept personally. I really like how that works. I find that's very cool. And then the third thing is known as the triangle inequality. The triangle inequality says that if I have a distance from point A to B and a distance from point B to C that will always be greater than or equal to the distance from point A to C. And the way to think about that is triangles. Is that my next? Yeah. Well, no, it's not actually. But that's that sort of triangle inequality is called the triangle inequality because, yeah, triangles literally follow that kind of rule. An equilateral triangle is a great example. Or just triangle in general. Anyways, whatever. It's called the triangle inequality. You can do the math. So here's an example of a metric. Specifically, this is a few, exactly, sum of two sides greater than the third. So, an example of metrics, first off, is our L1 metric. Or, it's known as a few different things. Taxicab metrics, as the crow flies metric, and it specifically says that I can only go in direct directions. I can only go over, up, over, down. That's it. So if I want to get from the green dot to the red dot, I can't drive diagonally through buildings. That's why it's called a taxi cab. It's the idea that you're laid out on like a perfect grid, like a city street. I have to go 3 up, 4 over, or 4 over, 3 up. There's no other way for me to do it, or that's the most efficient way for me to do it. I could also go like that, but actually 1, 1, 2, 2, 3, 3, 4. Yeah, it's the same distance. I can go like whatever. But that would be reaching this point, and then this point, and then this point, and then this point. A Euclidean metric, or two-dimensional metric, says green to red is only a distance of 5, because we're allowed to cut through diagonally. So that's why we get this concept known as the L1 ball. The L1 norm is this taxi cab metric, and we only care about this and this, because yeah, they're individual magnitudes. These individual points don't exist, because if I go from here, I can't end up on a regular circle's circumference, because I can't go to a point that's right here. I can only go to a point that's exactly on these lines, exactly where things intersect. So that's why it's a ball, but it does not look like a ball. And so, did I skip? Okay, I double clicked. So then, like mentioned earlier, see the similarity to, okay, and that says equation placeholder. Wow, this did not transfer correctly. Anyways, ignore that. So if we're in 2 dimensions, we then have the distance formula, which we can expand into, it is like train, yeah. I like that you got that. So this is another example of what we were talking about, where, so this is our metric. This is our equivalent to our row between X and Y in 2 dimensions, where this time our row is defined by this, our distance between XY coordinates. And now we could change this, we could expand it into higher dimensions, and that will change the formula, which I will show in a moment. But this is a great example of the triangle inequality. This right here is the distance formula and an example of how the sum of these sides will be greater than our hypotenuse. Yeah. This is where the visuals for that gets a bit more complex. So this is, but it's important to talk about it because it's important to talk about metrics. So we had determined then the L2 norm, and something that I find really important is notation. Because a thing that happened to me is I enrolled in a mixed undergrad graduate level numerical analysis course, and I had never seen the notation for the L2 norm before, and that had screwed me up. So then the professor was like showing different equations, and I was like, what is this? But everyone else seemed to, and I was gonna play. I was anxious, so I didn't know how to ask. I would then go on later to then the following year learn how to ask questions and be like, I don't understand. Yeah, so that's actually commonplace for our norms, because the single line will mean absolute value a lot. So like over here we have x of I squared means the absolute value or the magnitude of x of I. Namely, we don't care if this point is positive or negative, but we're gonna square it. And then the double line here we use to determine a norm. And that's where things get a bit tricky. You talked about the matrix notation being weird. That's the problem, is you only have so many things. And so you only have so many symbols. The determinant. Well, you see. Sorry, there's something in my eye. Yeah, so what it is sorry. So we have this issue with notation in the sense that, like vectors and matrices and whatnot, in a lot of analysis, you don't bother defining in the way that they're written out in linear algebra. X of I could be a matrix. X of I could be a vector. It won't be a matrix, it'll be a vector. X of I could be a vector, and so we care about the magnitude of that vector to then determine the magnitude, or the norm of the kind of like in between of the whole matrix of multiple different distance between multiple different vectors and whatnot. And that's what our L2 norm would be. And that is a subset of what we know as a P norm, where basically n dimensions, I don't know why they use P here, because we're used to thinking n dimensions, but then it's like, oh no, P dimensions, but it doesn't actually have to correspond to the dimension we're in. I could be in 15 dimensions and decide to take a 10th dimensional norm. Kind of whatever. It depends. What's the equation for moment of inertia? I don't actually know. Let me Google this. How so? I'm not actually sure. You have a vector with a column or row vector, why it be multi-row or multi-column? I think you're saying like, so if each x of I is a vector, then our collection of vectors, which we could make a matrix out of, will just be x in general. That's what I kind of meant by the notation thing. Is that you're gonna be worried that the entirety of a matrix will be represented just by an x, and the entirety of a vector will just be represented by an x of I, where I will correspond, say, to the number of columns, generally number of columns. We work less with rows. Generally, columns are what we work in for. Well, okay, that actually depends. Machine learning is a great example. In machine learning, you tend to work in columns are features, and then rows are samples. It actually has to do with how easily, I believe it has to do with how easily a computer loads a matrix. It's easier for a computer to load something with more rows than is columns. I don't know why that is. I wonder if what's the mathematics behind that? So v1 and v2 vector, they can just be divided by 3 or 3, but I use a vector when we end up with tensors. No, so the vectors will still be one-dimensional. I misspoke earlier when I said representing matrices. The vectors will still be one-dimensional. And then the matrix, the behavior of the entire matrix is what we'll use. It's just X in general. See, this is this is another example why in-person collaboration would be really important. Because explaining all this stuff over the internet without like a whiteboard to work on, where people can like write themselves, is awesome. That's why research groups are awesome. But yeah. So if we have, so like I mentioned, the p norm, and then we have the infinity norm, which is just the largest magnitude vector. That's all we care about. And here are the unit balls for each one. The L2 unit ball is our classic Euclidean ball. This is a weird LP ball, and then the infinity ball is just saying highest point, highest point, highest point, highest point. That's all we care about, is the furthest distances away, and as p increases, you kind of approach that. No, we're ending the near this. Oh, that's fine. It's gonna hop into the Final Fantasy one. That's good. So, moving on from there, that's by combining one of these metrics, which in a general sense is generally the one we are most commonly associated with, is the L2 or Euclidean metric, with a space, that gives us I thought I was gonna have a voice thing set up, a metric space, which we define generally by this x of p, x being our space, row, not x of row, x row, x being our space, and row being our metric. Generally, the form you'll see it defined in. But it is literally that simple. It's just, you define the space you're in. I'm in real numbers. I'm in n-dimensional real numbers, and I'm comparing things with a specific norm. That's how we get a metric space. There's lots of really, really cool metric spaces, and it's fun to try and make them, because the only thing is just you have to have a space, and then you have to have a metric that satisfies the triangle inequality. And there's like this really fun one that is like a donut, where it's like everything below a certain range is Euclidean, and then everything above the certain range is like exactly 2. If anything is like greater than 1, then the metric's 2. And so you have this weird donut metric where the entire space, everything below 1 is normalized, or is regular. Everything more than 1 is just this big circle. It's fun. I find it fun. If you like messing around with mathematics, or just messing around with that kind of stuff in general, then I find it to be a really fun thing to play with. And in the metric space, I forgot about what these next few slides are, so we're just gonna... Inside the metric space, we have a thing known as metric balls. Yeah, we skipped like 4 slides because they were just joke nonsense. And I'm not in much of a nonsense mood. I'm in a much more of a analytical mood brain right now. So these are metric balls. And metric balls, you know what, screw it, I'm doing it, are a member of my cohort would refer to these. Come on, you. As balls to infinity. That's how he described the entirety of the real analysis course. Simply as balls to infinity. Anyways, so a metric ball is yes, is it's best or easiestly visualized, most easily easiestly, I said easiestly. Most easily, I can't speak. I'm done with words. Is most easily visualized in 2 dimensions. And it's defined, first off, by a center point. Well, no, we need to find a few things first. We have a radius that has to be strictly positive. It cannot be even 0. Most Asian. Our radius has to be positive. All right, and then we have to exist in this space X, and everything has to be in this space. And in that space, we have a number of X of i's, and then Y. It's actually not necessarily polar coordinates. It is just meant to pull out even more. Pull out even more. It's just a space. You have a center point, you draw a circle. And these, it's simple. Metric balls are pretty simple, but they're important. They're the most useful tool, or one of the most useful tools when working in real analysis and metric spaces in general, because we use them in 2 different ways. Well, we use them in countless ways, but we define 2 different versions. Not even. Like, that's thinking computer science. That's thinking more example. No, it's literally, you could think coordinates. You can think a coordinate system. On a coordinate system, I have a center point, I draw a circle. Around it, we'll say an L2 ball. But I actually have an example in a second that you'll see. But, so what it is saying is that inside of this ball, we have an open ball where essentially the distance between everything, I'm pointing with my fingers, you guys can't see my fingers. It is literally just balls to infinity. Yeah. The center point, the distance between the center point and any of the green points has to be within the radius. And a closed ball it has to be within the radius, but it can also be on the radius. Not too bad. But if we do imagine it on an XY plane, that works as well. It's just saying that the the Euclidean distance, the magnitude between y and x of I, x of any of these, is going to be at a certain place. So I could draw a graph, and I'm just saying everything in there is a certain, because I can assign values. Each of these points is basically a vector. But 2D is the easiest, so we can just think of them as an xy point. Although the same concept actually does work in polar, but it doesn't have to be limited to polar at all. That's the thing. And our kind of final points are how we use these metric balls. These metric balls, one of the uses is for a set. And set theory is another thing that's actually more simple, and we know what how a bunch of set theory works. But hey Kikado, hi. Set theory is something we're familiar with. I just use polar to integrate balls. The thing about these balls is that we end up using them less in a literal sense and more in a analytical sense for... They're really useful in a lot of cool ways for proofs. And they don't always function the way you think they function. It's fun. It's fun. And it's beyond the scope of this presentation. But it is still an interesting thing, nonetheless. So, if we have a set E, well, that's the thing. That's a set is just kind of a a set is a mini chunk of a space. So, if you're just have a place that is full of stuff, a set is just a number of those things. It could be all of those things. It could be some of those things. It could be none of those things. It can be the empty set. So say we exist in a space, and within the space we have this black outline that we'll call set E. Alright? And then we choose a bunch of points x of I inside the set. These are these red dots. They're just random points in the set. Putting infinite balls in an infinite set, then putting infinite rulers in the same set. So, is set bigger than infinity, or is it all the same size? Well, it determines this. It depends on the set, really. That's kind of why set theory is very useful, and real analysis is very useful, because it is analysis of such a general thing. You can apply it in so many places. So, if I have these points and I have all these balls, then I can define these sets by saying a set is open or closed by if the balls stay inside. Can I draw infinitely small balls inside of this set? Where it's like, if I draw a thing here and I draw a ball around it, will there always be points in it? Can I keep finding smaller and smaller balls that get closer and closer to the border? That may be kind of out there, but think about it on a number line. If I have the open interval from a to a plus h, or a to b, x to y, 1 to 2, I can get infinitely closer to a without ever hitting a. I can get infinitely closer to a plus h without ever hitting a plus h. These are our boundaries. And that sort of getting infinitely closer is the drawing of these smaller and smaller balls. The you see it, yeah, so do you see how that open interval is just the one-dimensional example of this? Because that's all really open and closed sets are saying, and that's all an open interval is an example of an open set. Another just kind of like a basis for, math pun, another basis for how that works. On the flip side, a closed set. A closed set is determined by the opposite, but not exactly. It's determined by the existence of the open set. If we have a space, this space is our metric space, X. This green rectangle. Then our open set, that's supposed to say open, not set. I don't know why I wrote that. Anyways, here's our open set, E. Everything outside of E is therefore closed, if E is open. And again, we look at our number line for an example. If A to A plus H is exactly, that's exactly what it is. If A to A plus H is, if A to A plus H is the open interval, then it doesn't include A or A plus H. So then that means that negative infinity up to A, including A, is a closed, and A plus H to infinity, that is the complement and is therefore a closed set. The whole red stuff. It's everything that's outside of this open set. With that being said, it is entirely possible then to have sets that are both open and closed. Because if everything outside of an open set is a closed set, then it's possible to double up. That's why, if I remember correctly, the real numbers is both open and closed. And then, this makes you remember school time, Skikato. That's the goal. We're learning here. We're learning. Yeah, the real numbers is both open and closed, and then I believe the empty set, which contains literally nothing, is I think it's neither. I think it's neither open nor closed. Don't remember. I'd have to double check that one. But yeah, that's what something that I find is very cool about analysis, is that it's not, you get to get really creative with it. It's so kind of nothing in the sense that it's universal, it's abstract. Real number cannot be closed, it's always denoted with open brackets. That's thinking in a regular number line sense, but if we think about it, no, it's because I swear it's both. Let me double check. Is the set of... I'm pretty sure it's both. Yeah, it's both. It's because it has to do with limits that I don't entirely remember. But yeah, and because you want to think about it as the oh, now that I think about it, maybe the empty set is both open and closed then. Because the complement of the real numbers, if we're assuming we're only in that space, the complement of everything in that space would be nothing. And if the complement's open, then therefore that would be closed. But that's kind of the whole point, is that it is such a cool tool. I love it. Analysis is so much fun. If you really like just the weird, not even necessarily weird, well, yeah, in some ways weird, the interesting ways in which you can analyze everything. The real numbers exist in the complex set, so it has to go somewhere. That's if you're looking at it from the complex space. Again, yeah. You have to look at everything from a weird framework. It's in the same vein as, like, infinite versus countably infinite. The rationals are uncountably infinite. There's no way for me to real numbers are uncountably infinite. There's no way for me to possibly assign a counting system or, like, pinpoint a start or a finish or anything to the real numbers. But the rational numbers, it's entirely possible for me to say, this will be the first one, this will be the second one, this will be the third one, and go on from there. So therefore, they are countably infinite. Yet why mathematicians go insane? Yeah. And I think the reason a lot of people went insane in olden days, old school mathematicians, probably syphilis, but that's its own bag of worms. I guess not worms. Its own bag of germs. But Tish. Anyways. Since we've been running for about 2 hours, this last part I put up here just in case you're interested. If real numbers are uncountably big, then how can a set of complex numbers be bigger? Because there's more of them. But there's not actually more of them. It's the same way that we have different types of infinity. The reason you can't do something like infinity, you can't really use infinity to, like, do regular mathematics, to do something like algebra very well, is because infinity is a concept. And in theory, I can be further along in a number line than in a different place on the number line, but both number lines are going towards infinity. It's why we have to have stuff like L'Hopital's rule, because we don't know how the infinities are interacting. And so the real numbers are uncountably infinite in the sense that there's no way for me to know where it starts, where it finishes, where it anything, because it doesn't finish, but nowhere to know where it starts. I can't assign a start value really anywhere. Because no matter what, I can always add weirder and weirder numbers. The reason the rationals work is because I can essentially... A rational is defined by something like a fraction. A rational literally is defined by a integer over an integer. So I can have those integers, I can set those integers to count. I start the integers, one of them at 1, one of them at 0, and then I just have them both increasing by increments of other integers, and therefore I can start counting with them. You can't do that with the irrationals. Pi, I can't do anything with because it keeps going on, so I can't really define it as a basic fraction, although you can define it as a series, but that's something else. But then, 1.23751111525555567891 1 2 well no 10 not 10 1 0 1 2 3 3 3 3 1 9 9 9 8 7 6 5 4 3 6 8 6 7 5 3 0 9. That is not something that you can necessarily define by a fraction. We don't know. Probably not. So we don't bother setting a number to it. We can't count along it. That being said, within the complex numbers, the rationals of the complex numbers are countably infinite, I believe. Yeah, because you could just do the same thing. I could define the rationals and then define the imaginary component. And then from there, as long as I'm able to count a rational component and a rational real component and a rational imaginary component, then I can still count them. As I can define them both by fractions and have both the integer and the numerator and the denominator counting up in a consistent pattern. And boom, I've set up a counting sequence to count them infinitely. But if you're interested, I'm gonna leave this up for a minute. This is a good practice if you are unfamiliar with open sets, you're new to open sets, metric balls. So there's no fixed system. If I can prove something by weird maths, nothing is stopping me. Yeah. As long as it follows every criteria. Like follows, if it follows a triangle inequality, then the metric works, the kind of thing. There are a level of rules that you have to follow, but beyond that, you good. It's fun. It's why you can model so many weird things, and why you can model higher dimensions the way you can. It's the reason you can do machine learning, deep learning, all that stuff can exist because you're able to model these weird spaces, these weird feature spaces and whatnot. I love analysis. Also, if you are interested in learning more, so these are from my favorite professor's textbook, but the one I'm not about to show isn't his. This is a really, really good textbook. Obviously textbooks, I get them any way you can. I don't care. I'm not gonna be like, you should buy the official textbook. I didn't. I got a PDF of this shite. By Tom L. Lindstrom. It covers a lot of stuff. It's called Spaces. It's really good. I've read it. And it's really, really easy to understand. It covers a lot of concepts in a clear way. If you're unfamiliar with analysis, it might take a bit longer to grasp them, but I found it was very intuitive. So it covers metric spaces, it covers norms, it covers some Fourier analysis, it covers much, much more. It covers differential calculus, it covers the foundations of calculus even. It probably does a little bit with linear algebra, I don't particularly remember, but that's what math. See, that's why you want a math analysis. Another really good book. I forget who it's by, but another really good book is High Dimensional Probability, which covers like n-dimensional analysis in really fun ways. And that could be that's another similar one that could probably be really fun. But yeah, so I would recommend this one if you're curious about reading more. And finally, I like to close on something that helps my brain. And that thing is this. I didn't have a closing slide, but here is a video of a wheel spinning. I play it sometimes and it helps with my DHD brain. I will literally put this on 4 different monitors and I'll just sit there and disassociate so my brain can function. Oh, DHDA? Well, so as there are people in my life who are, there's a person. I've been told before that I don't have any form of ADHD. And I'm like, oh, okay. But I do have a deficiency that makes me hyperactive, or a disorder that makes me hyperactive, that causes a deficiency to attention. So, DHDA. I'll play this again now for myself. Yes. And that was the final slide I had planned. And right at the 2-hour mark, you know what? I think we're gonna go to closing credits while that song plays. But, as always, thank you everyone who stopped by. Thank you all for watching. It has been absolutely wonderful. I'm glad that I got to sit and yap, and I'm surprised that this presentation that really should have only taken like 15 minutes was able to be stretched out into 2 hours. Thank you all for watching. I will see you all next time. I've been Poisson, and bye-bye! This is a 10-hour video. Should I just let this run for the next 10 hours on stream and see if how many people sub during it? That's it. You know what? I'm actually gonna do that. Hold on a minute. This is so stupid. I'm gonna let this run for a while. No capture. Yeah, this is just gonna go. I'm just gonna set this here. I'll leave my computer. I'm gonna go make some food. Who knows if I'll be back. Here's this. emoji movie? I didn't. Perhaps it applies.